This video is going to look at partial fractions. What we mean by that is, if you look at the example, if you look at the calculation that's up at the moment, it's very easy to go from the left-hand side of this equal sign to the right. We can add equations or subtract equations really easily, make a common denominator, and we're there. What's a lot more difficult is going in this direction. If you're given a fraction, seeing how to split it up into two separate fractions, either added or subtracted. Now, why is this useful? Main reason is if you're given a fraction of this sort and asked to integrate it, you're kind of stuck. There's no obvious way of integrating that. If you're able to split it up into these two simple fractions, they both integrate a lot more easily. In this case, it's to be integrate a 3 ln mod of x minus 5 plus 5 ln mod of x minus 2. So getting it into that form makes your life a lot easier. There's three main types of partial fractions that you need to be aware of how to split up. And also there's a couple of different methods you might use for doing so. So we're going to cover all those in this video. Starting off with the simplest sort. So first example here, the simplest sort of partial fraction you might see is if you're asked, you've got something like x plus 17 over x squared, subtract x, subtract 6 here. What can we do in a sort of situation like this? Well, we're trying to split it up. If we want to know what's going to go in the denominator, we want to factorize as a very first step here. So if we look to factorize here, at least that'll give us a start. So factorizing that quadratic, this is going to factorize to x subtract 3 times x plus 2. And we've got x plus 17 on the top. So how do we think we might be able to split this up? Well, at the very least, we won't know what's going on in the numerator straight away, but hopefully we can predict what's going on the denominators here. We're going to expect that one fraction has a denominator of x minus 3, one fraction has the denominator of x plus 2, so that when we make a common denominator, we're getting that x minus 3, x plus 2. What we want to find is what's going on the top, so I'm just going to call them a and b here, and if we can find those constants a and b, we're in business. Well, how do we go about doing that? Let's use this as our starting point then, and let's go back and get a common denominator here. So if we get a common denominator in this situation, I'm turning it back into x minus 3, x plus 2. We're going to need a lots of x plus 2, multiplying the top and bottom of that first fraction by x plus 2, and then b lots of x minus 3. We can now compare what we've got here and say, well, the denominators are the same, we need to make sure the numerators are the same. So if we're saying that, comparing the numerators, we want to choose the values of a and b, so that x plus 17 is equal to a lots of x plus 2 plus b lots of x minus 3. If we find values of a and b that make that work, we're in business. Really, and mathematicians are lazy a lot of the time, and it's fine to be lazy. I should strictly be using identity sign there because I want it to be true no matter what the value of x. So I'm looking for the numbers a and b, so this is true regardless of the value of x. Two methods we can use. I'm going to show you my favorite method first, and then I'm going to show you an alternative method because in some partial fraction situations, it might come in handy for you. So first method is to say, well, if this is true, if we want this to be true no matter what the value of x, let's substitute some values of x in. What values of x are going to be nice to substitute in? Well, if we substitute in, so the first method is going to just be looking at doing substitutions. If we substitute in x equals 3, what does this identity become? We get on the left-hand side, we get 20. And on the right-hand side, we're going to get a times 3 plus 2, or 5a. And then the b term disappears. So that x equals 3 is a really clever choice of substitution there because it makes this second term disappear entirely. Definitely a good idea for us. Because we get this, and straight away we've got a equals 4 with no problems whatsoever. What else would be a good value of x to sub in here? If we sub in x equals negative 2, then that a term is going to disappear entirely. So on the left-hand side, we'll get negative 2 plus 17, or 15. And on the right-hand side, we'll end up with minus 5b, and we'll get b is equal to negative 3. So at this point, we can say, well, hang on, we've got values of a and b, so our answer is just going to be 4 over x subtract 3. And then we could put plus and negative 3 on the top, but it's going to be nicer to put subtract 3 over x plus 2. And that is our answer to the question. That's what we're considering the partial fractions. We've taken this fraction and split it into two simpler fractions. And if we wanted to integrate those, we wouldn't have a problem doing that. The second method, which, like I say, most of the time I wouldn't go for, but it's worth seeing, it's worth being aware of, because there's certain cases that'll come up in more complicated situations where it's worth seeing this, is to say we've got an identity. Let's rewrite this right-hand side. So we do need to do some expansion. So ax plus 2a plus bx subtract 3b. If this is an identity, the coefficients of x must be the same on both sides, and the constant terms must be the same on both sides. So this is looking at coefficients, or comparing the coefficients. So the coefficients of x on both sides, the left-hand side, the coefficients of x is 1. The right-hand side, we've got ax plus bx. So we need 1 to equal a plus b, and then we can look at our constant terms, and we've got 17 on the left-hand side and 2a minus 3b on the right-hand side. And boom, you've got simultaneous equations. Just go through, solve those on your way. I'm not going to worry about going through and solving those. I'm backing it from there. You could even use your calculator when you get to that stage to do that if you so wanted to skip those steps. Okay, so that's the first sort of partial fractions you might come across here. You're given something where you can factorize the denominator, split it in two parts like this, and you're away. The next level up would just be, I'm not going to go through all this example, we're just going to give a start. What if your denominator had three factors instead? What if it was maybe x minus 3, x minus 2, x plus 1? And there could be anything up to a quadratic on the numerator, so I don't know if this is going to work here with nice numbers. It would be possible to get them, but they might not be nice. If you had something like this, possibly predictably here, you just try something over x minus 3 plus something over x minus 2 plus something over x plus 1, and then make your denominator x minus 3, x minus 2, x plus 1, and compare your numerators and go from there. So very similar to this step, as long as it factorizes nicely and you've got distinct factors, you're going to go exactly the same as before. I would recommend always writing out these two steps here. It's really tempting to skip these steps once you've done a few questions like this, but it will make it really clear for you and stop you switching your A and B round and make sure you get your denominator right. Really common mistake is to get your A and B switched around at some point here. Doing this will help you avoid that. Okay, so what else might we get here? One more complicated questions could we throw at you here? So far, we've looked at what happens if we've got all distinct factors. It gets more complicated if we have repeated factors on our denominator. So let's consider what we've got 3x plus 5 over x plus 1 squared times x plus 2. In this situation, the first tempting thing to do might be, based on what we've seen, might be to go for three fractions, and you do ultimately need three fractions here, and say, well, we want denominators of x plus 1, x plus 1, x plus 2. If you try this, you'll find you run into issues, and if you do the substitution method, your solution just straight up won't work once you've subbed in your two values. You'll be able to get one value, and you'll be stuck finding the others. The reason for that is these fractions here are kind of doing the same job. We've got a constant over x plus 1. They're almost doing the same thing there. But we do need two fractions to give ourselves enough freedom to satisfy the conditions we need to fill in when we go through either substitution or comparing coefficients. Now, what we can notice here is on the right-hand side, the common denominator of the right-hand side at the moment would just be x plus 1, x plus 2. How can we make it so the lowest common denominator is x plus 1 squared, x plus 2? The solution for this, which is definitely not obvious until you explain it out, is to make one of those fractions x plus 1 squared. So whenever you have a repeated factor, you can have one fraction where that repeated factor appears as a repeated factor, so squared, and another fraction where it appears on its own. This is now going to give us enough freedom to go through and solve the problem. So at this stage, we're going to mimic what we did earlier. So we're going to rewrite these all as one single fraction with the same denominator as originally, x plus 1 squared, x plus 2. So what will we get on the numerator here? We're going to get a lot of x plus 2, multiplying top and bottom of our first fraction by x plus 2. Our second fraction, we need to multiply top and bottom by x plus 1 and x plus 2. And our third fraction, we need to multiply top and bottom by x plus 1 squared. So now our denominators are the same. We can now compare our numerators and get into the same sort of situation as before. So comparing our numerators, we've got 3x plus 5 is identically equal to, and don't, if you just write equals to here, it's absolutely fine, accept it that you might do that. And on this side, we're going to get a brackets x plus 2 plus b, x plus 1, x plus 2 plus c, x plus 1 squared. If you wanted, you could use comparing coefficients straight away here, looking at your x squared terms, where we have 0 on the left-hand side, our x terms and our constant terms. But that means we need to do a bunch of expansion in the first place. Again, our life's going to be easier if we go for substitution. It's personal preference, but I'd highly recommend the substitution. What's going to be one good value to substitute into the right-hand side? Well, x equals negative 1 will make two of those terms appear. So let's go for that. If we submit x equals negative 1, the left-hand side is going to be negative 3 plus 5, or 2. And we're going to get a times negative 1 plus 2, or just a times 1. And then the second term is going to disappear because the x plus 1 is 0. The third term is going to disappear. And there we go. We've got a equals 2 straight away. Much easier than doing all the expansion. What else could we substitute in? Well, x equals negative 2 is going to make two of them appear. So if we sub in x equals negative 2, we'll get negative 6 plus 5, or negative 1. And then we'll get equal to, the first term will disappear because x plus 2 is 0. The second term will disappear. And we're just left with c lots of x plus 1 squared. Well, negative 2 plus 1 is negative 1. Squared is just 1. So we just get 1c there. So again, we've got our c straight away. At this stage, we don't have an obvious value to substitute in to get b. That's going to make the other things disappear. You could compare coefficients on this side and get to the next expression with b, but again, to avoid any expansion, it's going to work for any value of x. Let's pick the easiest possible value of x and see what we get. Let's sub in x equals 0. If we sub in x equals 0 here, what are we going to get? On the left-hand side, we'll get 5. On the right-hand side, we've got a times 2, so 2a, plus b times 2, because it's b times 1 times 2, so plus 2b, and then plus c times 1, so plus c. But we know our a and our b, so we can sub those in now. So 5 equals 2 times 2, which is 4, plus 2b, subtract 1, because c was negative 1. And at this point, we've got 5 equals 3 plus 2b, so 2b is equal to 2, and b is equal to 1. So look to sub in the things you can that'll make your life easy, and then you can deal with the difficult bits at the end by substituting any value of x you want, but you might as well keep your life easy. So our final answer, going back to the start and subbing in, is going to be a, which was 2 over x plus 1 squared, and then plus 1 over x plus 1, and then subtract 1 over x plus 2. And that's your answer as partial fractions right there. So at single math A level, those are the only sorts you're going to see. So just to categorize those, you will either get a situation if you have something where it's just two distinct factors on the bottom, you can just split it up as something over the first factor plus something over the second factor. If you have a situation where there's three distinct factors, then you just get an extra fraction with that other factor there, and so on, but you're not going to get one with more than three factors. And then if you have one where you have a repeated factor, something like x minus lambda squared, x minus mu, and your numerator has to be of a lower order than the denominator, but your numerator could be up to a quadratic here. It'll be a separate video for polynomial division for how to deal if it goes beyond that. Then on your numerator here, you're going to need three fractions, but you're going to have one fraction where you have your repeated factor squared, one fraction where you just have one made up your repeated factor, which is a single factor, and one fraction where you have your other factor, and then you're away setting up the question. Hope that helped. If you are doing further maths as well, then there's going to be a separate video in the further maths playlist looking at how to do one extra sort of partial fractions you need to be able to deal with.